This is the fourth video on the National 5 topic of similarity. In this lesson we'll be looking at further similar triangles. What I'd like you to do here is to attempt to fill in all the missing angles on the two diagrams. Two key features to notice are the fact that these lines are parallel and that these lines are parallel as well. So what I'd like you to do is to pause the video and try and fill in, using your angle facts, all the angles in each diagram. Right, the key to this is looking for various F, Zs and X shapes. To give them their proper name, I suppose highlighting this F shape first gives us what's known as a pair of corresponding angles. I know using this F shape I can form these corresponding angles. So the top angle equals the bottom angle here. So I know both of these are 93 degrees. So what you would have called F angles, we're really calling corresponding. I can find this angle in my triangle here because, well, I know the angles in a triangle all add up to 180. So I'm really just concentrating on this bit of the diagram. Adding them up, 28 plus 93 would give me 121, and the angles in a triangle add up to 180. So the difference there would give me 59. So I know that would be 59 degrees there. Again, if I look carefully using the parallel lines, I've got another F, another pair of corresponding angles. So it means this top angle here will match this bottom angle here and be 59 degrees too. I've got two angles left over. Looking at this one here, well, I've got two angles on a straight line. Two angles there forming a straight line, a straight angle. So they have to add up to 180. So 59 plus 121 would make 180. Same over at this side. 93 and this angle in here, that would form 180, form a straight angle. So 93 plus 87 would make 180. On the second of the two diagrams, no real F shapes, no alternate angles. But if we look, I have this Z shape. So what's known as alternate angles. So I know that 32 degrees matches with this one at the top of what you might have called a Z angle before. But the proper name is alternate angles. I could take this Z and I could flip it as well. It doesn't really fit. And I've got another Z there, showing me that these two angles are the same. Now, to fill these in, I'll need to figure out what one of those is. Looking at the top part of the diagram, looking at A, B, C, looking at that triangle there, well, I know two angles in the triangle, so they'll add up to 180. 88 plus 32 is 120. Taking that away from 180 would be 60 degrees. So I know I have 60 degrees there, and I know I have 60 degrees there. My missing angle in the top there, well, I can look at it like this. Two lines crossing over at a vertex, at a point. So I've got what's known as vertically opposite angles. So this angle in here will be 88 degrees. The purpose in this exercise is to show you, looking at the first one, I have a triangle here with angles of 28, 93, and 59. And I've also got a triangle here, so the bigger triangle. Again, look at his angles, 28, 93, and 59. The triangle UST, the top small one, and the triangle UQR have got the same angles, so they're mathematically similar. Triangles UST and UQR have equal angles. This means they're mathematically similar. The same is also true for ABC, so the one on top. Looking at this angles match up, these angles match up, and these angles match up. So that means those two triangles are mathematically similar. So it just means sometimes we need to look very carefully to find similar triangles. And by finding similar triangles, we can deal with some more complex problems. But like this one. So there's two parts to this. I've been asked to prove the triangles in the diagram are similar, and hence use that fact to find the length of those two sides. So first things first. I know this angle and this angle have to be the same. That's they're vertically opposite on the other side, on opposite sides of a vertex from each other. 104. I know, using my parallel lines, that these two angles are the same. So this would make this 29 degrees here. I also know, using parallel lines again, these two would have to be the same. I would need to calculate that for myself. But yeah, notice both the triangles have got two angles. So 104 plus 29 would give me 133. Subtracting that from 180. Well, 80 take away 33, give me 47. So we would know these angles here are 47 degrees. So both triangles have equal angles, so they are mathematically similar. Now, what I would recommend here, just to make things a bit easier, is I would take the triangle ABC, so this one here, and I've just redrawn it. So I've redrawn it so it's sitting flat, all the angles written down. And I would take CDE, so the smaller of the two, and I've also redrawn him. The reason for that is it makes it very easy to find which sides correspond with which. I've been asked to find two sides. I've been asked to find AC. I've been asked to find this side here. So it's on the larger of the two. So I'm going to find a scale factor of enlargement. So I've got two corresponding sides, the 20 and the 12. So my scale factor of enlargement would be 20 over 12, gives me 5 over 3, a number bigger than 1. So that's a scale factor for enlargement. So to find AC, I need to take its corresponding side and multiply it by the scale factor. So AC is equal to the corresponding side, which is 6 long, times my scale factor. Uh, Long way of doing this, 6 times 5 would give me 30, divided by 3, 10 centimetres. The second part, find BD, a bit trickier. Well, on my second triangle I've got D with no B. This first triangle, it's got B with no D either. But if I look back to my original diagram, I've been asked to find all of this. Notice, I know this already, so I would really just need to find that there. So, I need to find this line CD. So, CD is on the smaller of the two triangles. So I would be finding a scale factor of reduction. Again, using the two corresponding sides, like so. And that would give me a scale factor, once I've simplified, of 3 over 5. Notice it's the enlargement scale factor flipped. I'm trying to find CD, so I take his corresponding side and I would multiply that by the scale factor. So CD is my corresponding side of 15 multiplied by my scale factor. You could 15 times 3 divided by 5. Might be a bit more sneaky with it. Divide by 5 first. Give you 3 and 1. 3 times 3 is just 9 centimetres. We're not done though. Look back at your original diagram. We've been asked to find all of this length here. Okay, so I know BD is BC plus CD. So I just need to remember to answer that. I've needed to add the 15 here to the length of this side here, which is what I figured out.